battery energy storage systems BESS are prone to blast or fire or failure due to burnouts of printed circuit boards.
All this thing is being how heavy they are. Oh my god, that scared the me. I'm gonna bleep that out because that scared me. Dude, I got that on video. No way, you got it?
Why does fire catch in BESS? The fire starts when there is excess heat generated inside the battery. Lithium batteries catch fire if the charging current is supplied beyond 65 degrees C or below 0 degrees C. Lithium batteries catch fire if discharging current is present above 80 degrees C or below minus 20 degrees C. The lithium battery will catch fire if direct sunlight heats up the battery unit beyond 60 degrees C. The battery management system BMS is the weak point of a BESS. The BMS will be present in general in 3 levels inside the BESS. Fire will result if the BMS allows batteries to get charged when the temperature is above 45 degrees centigrade. There are 3 types of BMSs in a BESS. First is a pack BMS. The pack or battery has a voltage of 51.2 volt. Then comes the BMS of the rack. It is also called the high voltage box. The voltage will be high up to 1500 volts. And the last is stack BMS. It is also called intelligent BMS. It also has the highest voltage and the highest current rating. The pack BMS, also called as BMU, is a slave BMS. The main function of the pack BMS or BMU is to provide a limited amount of cell balancing, and also it has a CAN signaling interface which is optically isolated and connected to the other BMSs. Rack BMS. The second type of BMS is called the rack BMS. It is also called as the high voltage box with a rating of say 1500 volt, 314 ampere hour. The DC circuit of the series connected batteries go via this rack BMS towards the inverter. This BMS can switch off the rack battery current in case of alarming conditions. Stack BMS. This stack BMS will be required if we connect more than one rack batteries in parallel. If we do not do the parallel connection of the racks, there is no need for this stack BMS. The rating of the stack BMS will be having the highest current and the highest voltage. For example, 1500 volt, and if we connected 4 racks, each of 314 amperes, the current rating will be 1256 ampere. The stack BMS knows everything that goes on the BESS and does the overall management. The DC path in this BMS going to the inverter can be switched off by a series connected MOSFET inside this BMS. The signaling link from the stack BMS can feed all monitoring data to an energy management system also. Why blame BMS for fire in the BESS? In the picture, you see there is a link between the inverter and the master BMS of the battery. This link is a CAN signaling link. If it is failed for any one of the three reasons, there is a mechanical link break, or the link is not compatible in software or in the signaling, that is the inverter is not compatible to the battery, or even if they are compatible, the person who installs, if he has not configured both sides of the link properly, then the link will not be operational. If the link is not operational, it can lead to fire in the BESS. How? Actually, the BMS tells the inverter the battery temperature and asks for current derating via the CAN signaling link. But if there is a CAN signaling failure, it can result in fire. Will a BMS be capable of derating the DC current as a function of the temperature? Unfortunately, the answer is no. All it can do may be to switch off the DC current in the BMS PCB in case of high temperature, but it cannot do the continuous derating function. The derating function of the current is in the inverter mainly. So only the inverter is the source for controlling the charging and discharging current of the BESS and not the BMS. The safe temperature range for charging of the lithium batteries is from 0 degrees C to 45 degrees C. For discharging, the safe temperature range is from minus 20 degrees C to plus 60 degrees C. This picture shows the current derating required when the lithium battery is charged. You see that the charging current should be derated, that is decreased from 45 degrees C above, and the current must be made 0 at 65 degrees C. What is the problem if you connect two batteries with dissimilar voltages? For example, if you connect a 12 volt car battery with a 6 volt car battery, what will be the resultant voltage, output voltage? Will it be A 12 volt, B 6 volt, C 9 volt, or D none of the above? The answer is none of the above. Let us study more what will happen if you parallel two batteries with two dissimilar voltages. Parallel connection of two batteries with different voltages is equivalent to a short circuit. Thousands of amperes can flow and the current is simply limited by the internal resistances of the battery. In this example, I am showing the current is around 100 ampere, but if the internal resistance are small, the current will be very high. It can be up to thousands of amperes. What will happen if you connect two rack battery banks in parallel? Actually, this is a wrong design. The DC circulating currents of the order of thousands of amperes will occur from one rack to another. The BMS PCBs may burn out due to the large transient circulating current at the time of switching or parallel connection via the two rack BMS PCBs. Life-threatening issues in BESS design. 1. Do not use parallel connected racks of battery banks. This will create hidden DC circulating currents that will lead to either fire or failures or degradation of the batteries. Point number 2, make the BMS design compatible with the inverter used like Deye, Solis, etc. with CAN signaling working as per the inverter requirement. Failed CAN communication due to incompatibilities between the inverter and battery BMS can lead to fire. Point number 3, Do not leave the BESS battery design to the BMS manufacturers, as their software may have unchecked faults. Understand CAN signaling yourselves and test everything yourselves. Point number 4. At the time of installation by your contractor, conduct 100% check that the CAN signaling link is operational between the inverter and the battery. Point number 5. Use air conditioners or heaters in the BESS containers to provide the best operating temperature for the batteries for long life and for no risk of fire. The issues in a BMS. Point 1. BMS hardware and software are proprietary. Point number 2. BMS boards of battery and the BMS of inverter may not be compatible. Point number 3. Some BMS vendors do not give standalone BMS hardware but want to give the total hardware and software tailor-made as a complete package. This makes integration of third-party batteries difficult. Point number 4. The energy management system, EMS, needs data from and to the BMS as well as the inverter, and the proprietary nature of the inverter and BMS make the life difficult. Point number 5. Burnouts of BMS boards is a major problem due to improper design of the overall design of the BESS. Point number 6. Balancing of the cells may not be adequate by the level 1 BMS. This will lead to large circulating currents from one rack of batteries to another rack of batteries when connected in parallel. Fire or burnouts or degradation of battery life will result from this. Point number 7. BMS boards do not implement current derating function as a function of temperature above 45 degrees C. This can lead to fire in BESS in hot summer, particularly if the CAN signaling link to the inverter is not functioning. Point number 8. Only very few high voltage BMS manufacturers are available, like GCE, Udon, BMS PowerSafe, Novation Energy, etc. Point number 9. CAN communication and software among inverter manufacturers like Deye, Solis, etc. are proprietary in nature, leading to integration issues with OEM BMSs that may lead to fire. Point number 10. BMS is a weak element in the overall BESS design, and this is an international problem in that no reliable BESS can be designed with the best quality at least cost. Standardization of the BMS and inverters is the need of the hour. Point number 11. The maximum power capacity of one inverter box is now limited to 125 kilowatt, both from Solis and from Deye. In the design, always use inverters with the highest power capacity to reduce the number of inverters in parallel. BESS design is difficult with the proprietary nature of the CAN signaling or software of the BMS manufacturers and the inverter manufacturers. EMS issues. Point 1. The high voltage BMS manufacturers give a touchscreen display to monitor cell voltages and cell temperatures, but no configuration commands to the BMS can be given from this touchscreen or even via CAN signaling from the EMS to BMS. Point number 2. The inverter manufacturers provide a touchscreen display that act as mini EMS, but confusion will result when we use 500 inverters in the BESS, software is not available for handling CAN signaling from these many inverters to the EMS and the CAN signaling from the BMS of the batteries to the EMS. So these are the software issues for the EMS. Conclusions. 1. Do not parallel racks of batteries. 2. Avoid untested BMS tailor-made for you. 3. Bring standards and specifications of the inverters, PCS, BMS, high voltage batteries, EMS, and the CAN or RS485 signaling to bring uniform compatibility among different vendors. This is very much required for the prosperity of this BESS business worldwide. 4. Make 100% sure that the derating of charging and discharging currents in the batteries as a function of temperature is provisioned in the inverters and the BMS, and this function is working. Thank you.